The Equipment and Measures page contains a lot of information. Let's take a minute to just talk about how this page is set up. One of the first things you'll notice are the red dots that are shown here. This just means that the information on this page hasn't been saved yet. We won't be able to progress until we save the information. If we look at the overall structure for how this page is laid out, we're going to end up seeing that all of the alternatives will line up across the top here. So we only have the baseline alternative at first. That's the only one that's here, but after we add the base case and additional alternatives, this line will start filling out with all of our alternatives. And you can click through those tabs to work on the data for each one of the alternatives. Here on the left, you'll see our two building clusters that we just created a minute ago. We've got our centralized buildings and our decentralized buildings. We can click between these two to look at this equipment list for each one. Alright, so let's take a minute to talk about the equipment list. That's the heart of this page. And really it's a giant table with information relating to technologies that you might want to look into for large groups of buildings. Since it's a little bit easier to talk about, let's start with the decentralized buildings. So our decentralized buildings aren't connected to any central plant, and since we're in the baseline, we just want to describe the current as-is situation with how those buildings are receiving their heating, cooling, and electric power. So one thing you can do on this page is click this magnifying glass button and it will blow it up the table to make it a little bit larger and easier to work with. Alright, now we can look at most of the columns here. So again, going over this table, if you look at the rows here, each row represents a piece of equipment. So here the top row is related to boilers, and specifically distributed boilers. So this relates to boilers at every one of the buildings in the cluster that we're talking about, or the cluster that we're currently highlighting there on the left from that previous page. Similarly, the next piece of equipment is related to the chillers, distributed chillers for each one of those buildings. Continuing down the list, we see solar PV systems for various sizes, the AC bus, here just basically the electrical equipment that's connecting us to the grid, and then a large number of pieces of equipment that are related to central plants. So we'll kind of break off the list right here, and looking down, starting at the index number 7, we see central plant boilers with different sizes. Here the output capacity is going to determine what the size is for the piece of equipment. Reciprocating engines, this is just a natural gas engine, very much like a car engine, but running on natural gas and being used primarily to produce electricity. We have reciprocating engines that also capture with waste heat recovery equipment on them, so you can do cogeneration, producing power and heat at a central plant. Natural gas turbines just for electricity, and then further down here for electricity and capturing waste heat. Electric chillers that are air-cooled, again these are larger pieces of equipment, something for a central plant, not necessarily building scale. Absorption chillers that are single stage, and then dual stage absorption chillers. You may not have heard of all of these pieces of equipment. It wouldn't be uncommon. These again are specific to central plants and uncommon at this scale, at least for buildings. Electric chillers that are higher efficiency electric chiller, organic Rankine cycle turbines, just a lot of different types of equipment that can be looked at and analyzed for use with multiple buildings. Now if we scan back up to the top, let's go ahead and talk through these columns. So the first one is just an index number, and then a generalized equipment type, and an equipment name. And these are really just for the user, just to provide some clarity. It's not going to change any outcome. They're editable. You can add information to them. Well, let's go back and reorder by index. For example, you can say these are the existing distributed boilers. And you may want to make some kind of note in the equipment that will remind you of something later on in the study. So going across, we have a maximum number, and this is more important when we go to central plant equipment. It'll make more sense in a moment, but this is basically the maximum number of this type of equipment that could be included in the solution. The output capacity, and here you can see these are just very large numbers. The capacity isn't required for decentralized systems, only for central plant equipment. So here we're going to assume that whatever system we're buying, whatever system we're talking about here for boilers for each building, we have enough capacity to meet the loads. So that's a sizing issue. We're going to talk about sizing distributed equipment in another video, and it will give specific information on how to cost that equipment as well. We have inputs and outputs for each piece of equipment. So just a single input and then multiple potential outputs. Here for these boilers, they're going to take in retail natural gas. And you can see that word retail is separate from other natural gas inputs, primarily because, as we found through doing a number of these studies, the natural gas cost for natural gas delivered to individual buildings is commonly much higher than natural gas costs delivered directly to a central plant. Many times there's a whole different rate because they're using a large pipe to deliver a lot of natural gas. The overall cost for that fixed infrastructure that had to go into it is much lower when you're using a lot at a central plant than it is for those smaller distribution pipelines that are going around in installation. So we've actually broken out two different costs there. And then hot water distributed to buildings, that's what you're going to get out of distributed boilers. And then similarly, the chillers, if we had scanned to the left, the second line is related to distributed chillers. They're going to take in electricity from the grid, and really that's going to be from our AC bus. We could be working with renewables or something else, but this is basically saying that we're taking in electricity and putting out chilled water that's distributed to the buildings. Now, this longer term is just to differentiate. We could be producing chilled water at a central plant, and then we would need a network, which is going to be a different piece of equipment or a series of pipelines that would bring that chilled water to the building. So we're going to continue on to that. That's part of this tool, but those are going to be two different things then. Chilled water at a plant needs to be distributed, or chilled water there at the building. All right, if we continue to the right here, we've got multiple outputs, and that's going to come in for some of the other pieces of equipment. As I mentioned, we had cogeneration engines and turbines that would take in natural gas and output electricity and heat. So that's why we've got multiple outputs, and there are some other things that could output even more than two different types of energy. And here we have the efficiencies. So basically just converting from the first input to the first output, and then to the second output, the third output, all the way across. So just linear conversion efficiencies between the input and the various outputs. So here, to interpret this one, it's 85% efficient to go from the natural gas to the distributed hot water for the buildings. Now, you can change these numbers as well. So if you know that we have condensing boilers, you may be able to increase this number for the distributed boilers up to somewhere around 90 or 91%. If you know these are older boilers for your group of buildings and it's all a relatively homogeneous technology, you could decrease this number. But it's within that range. You might go down to 80% or even a little bit lower. But this gives you a starting point, and if you've got better information, you can always go in and edit that number and leave that in here for even closer results. Now, because this is existing equipment, we're not going to put any installation cost associated with it. We will have annual O&M costs. And within that other video I was mentioning, we're going to talk about how to cost these and how to provide estimates for annual O&M costs. There are two main sources you can get this annual O&M cost from. The first one would be directly from installation personnel. If you can talk to them about any equipment maintenance contracts or any information they have related to the operations and maintenance in terms of labor and parts, not in terms of energy, then you can roll those numbers up and put them here. So you could enter it directly from that information. If you don't have it, we're going to go through a process where we would estimate the installation costs for for the number of boilers or chillers, whichever systems we're working with, that we would need for the buildings in that cluster, and then from there take an estimate of what the annual O&M costs would be. So that'll be in a separate video, and we'll come back to that later on. Then we also have an approximate lifetime for each piece of equipment. Okay, so for now we're going to go ahead and leave this information as is. As I mentioned, you'd come back through here. The only thing that would have to be changed normally would be this annual O&M cost. So you'd get that from the installation or from estimates that we'll go through later on. But otherwise, this study is all set. We've got the heating equipment, or this cluster of buildings, the heating equipment and the chilling equipment, and we're just going to be getting electricity from the grid. So there are no other changes that need to be made here. We can go ahead and hit the X, and we're done with the decentralized. We're still going to have to make some changes to the centralized system. So let's click on that one. You don't have to save when going between the clusters. You do have to save before you continue on to the next tab. Alright, so here, these centralized buildings for this cluster don't have any distributed boilers. We're going to set those to 0. They do have distributed chillers. And again, we're going to hold off on changing that annual O&M cost, but that would be something that needs to be changed in a normal study. When we look at the central plant, we're going to be able to collect information on what equipment is present. And so here we're going to take that information and translate it into this equipment list. So in going through the central plant for these buildings, we're able to determine that there are 4 of these boilers, central plant boilers, that are approximately this output capacity, this 10,000 kilowatts. Now, most central plants that you go to, they're not going to tell you the output capacity in terms of kilowatts, but they'll tell you it in terms of something that can be converted to kilowatts. So it's always going to be some power, some energy per time factor that can relatively easily be converted into this common set of units. So here it happened to be this size, directly a size that's already in the system. If it was another size, it would be very easy for us to change that number according to the size that they have for that central plant. Alright, if we scan across, there are other things that we can change. So this is going to take in natural gas. This is very common. If we have a central plant, it likely has natural gas driven boilers, and they're going to put out some temperature of heat. And so if you want, you can actually change the output temperature for the boilers to the appropriate temperature that central plant is operating at. So there's a number of central plants that operate around this temperature. This is kind of a medium temperature, medium to higher temperature. But there are other places, other temperatures they could be running at. And that becomes more important for some of the other equipment. So some of the equipment can only run on higher temperatures or higher pressures. Here we've got an associated temperature and approximately what the saturated steam pressure would be related to that temperature. And so that's kind of why you see these two numbers here. We've got a pressure over here, 120 psi, and a temperature range, about 350 to 375 Fahrenheit. Okay, but you likely don't have to change this at all. The only things you'll need to change are the costs. So one other thing that I didn't mention, you can actually, we'll change this back to 0, you can copy these pieces of equipment so that you don't have to change anything in the list. If you'd prefer just to have a whole nother piece of equipment down at the bottom, you can click this copy, and it's going to pull it down to the bottom, and actually it already pulled over that 4 for us. There are 4 boilers. Alright, with that 10,000 kilowatt capacity, taking in natural gas and putting out this temperature of heat, we have an approximate efficiency of 88% or 0.88. Now because these boilers are existing in the baseline for this centralized building cluster, we're going to take away this install cost. We're going to put it down to 0. Now again, we would need to adjust the O&M costs. Here though, we already have some estimate of the O&M costs for a boiler of that size. Now, if it wasn't that size, you could just scale the O&M cost, the estimate here. Obviously, again, the best, most precise way to do this would be to get the data directly from the installation personnel. They may have the information on O&M costs related to that equipment that you'd be able to divide down per piece of equipment. Here, this cost is per each boiler. So there are 4, it's going to be multiplied up for the total set of boilers. But here, again, this is partly related to running that central plant that's going to need some operations. There's going to be turnover and that sort of thing as well, controls and everything else. So those costs are associated with those boilers, and then a lifetime as well. If you have actual data, you can enter it here, and because it's a specific piece of equipment, we can use as a default number this annual O&M cost associated with the O&M costs of a new boiler of that size. Alright, so we've put the boilers in. This is approximately the size that we would need. Now we're going to go over to the storage tab. We didn't have to do this for the decentralized buildings. There wasn't any storage built in. They didn't have any networks. They just had decentralized equipment. Here we do have storage, or I should say our network acts very much like storage. It's a large pipeline filled with a lot of water. There's a lot of heat capacity in that water, so it works well to model a network as storage. So let's go ahead over there. I'm going to click on that tab and look at the technologies in this list. So here primarily we have chilled and hot water storage tanks of different sizes. So just like the other list, we have a number of sizes for each technology. And that's so that we can have economies of scale come into play. So the costs are going to go down. The costs in total are going to go up, but the cost, say, per capacity is going to decrease for these larger systems. And that helps us with the generalized sizing. Okay, and then down here near the bottom, we have a low temperature hot water network, a high temperature hot water network, a steam network, and a chilled water network. Now for those buildings, the centralized buildings, they're only on a hot water network. They still have distributed chillers. Now if we look at the temperatures for these networks, we're going to select this one. We're going to say they do have a hot water network. And I'm going to select this one because the temperature is the same temperature as our boilers, but more specifically, it's the temperature of that central plant. So we get that information by talking to the personnel at the central plant. Hopefully, some of the operators of the equipment, you can find out what the equipment temperature is running at, what are they distributing water at, what temperature, and you can enter those in here. If it was a different temperature, we could change that here as well. All right, the output capacity, again, kind of like the distributed equipment, has been set arbitrarily high just so that it doesn't limit the output. That's not going to be a factor in our calculations. As we go across here, we can see an efficiency. So this is like a throughput efficiency, how much energy is lost passing through. And then we also have our installation costs, which is 0 since we already have this in place, an annual O&M cost, lifetime, and 2 fields that we didn't have in the previous table, in this input-output table. And that's because these fields are associated with the storage itself. So here we want to know how much thermal energy storage we have in that network. I'm going to have, again, a separate video that will go into greater detail here. So we're going to stick with the default for now, and we'll refer later on when you're having to deal with these networks, which aren't going to come up all that often, but we're going to need greater information or a larger amount of information to make these kind of determinations. So for now, we're going to stick with the default on storage here. Again, we'll have that video to show the detail for costing networks and for determining the amount of storage. And then the final column is the standby loss. So this is the amount of heat loss we have that's just continually going on. So this would be the heat that's lost through the pipe, out just usually into the ground, or in other situations we're just generally continually losing some amount of heat in this network system. And all of these numbers are adjustable, and just like the distributed systems, these numbers really need to be changed or need to be looked at more closely than some of the large-scale pieces of equipment. So, for example, just to make this point more clear, a boiler of a certain size performs about the same in a number of different locations. The efficiency might change a little bit depending on operating temperatures and on, say, input temperatures, outdoor air, and that sort of thing, but it's within a fairly small range. Now, something like, and again, similarly with cogeneration engine or something else, all those technologies operate for a given size. If it's, a 10,000 kilowatt system or something, it's going to operate relatively similar in different areas, and it's going to cost a relatively similar amount of money. And that can be multiplied up by some kind of area cost factor that would be dependent on location, but at least it's within a relatively small range. That idea is very different for networks, centralized networks, and distributed equipment. So if we're working with a building group or a building cluster of 10 buildings that are on a network, that's going to be a very small network. If we're working with a building cluster of 150 buildings, it could be a very large network. We've seen systems of around both of those sizes, and so we need to do specific calculations to determine the size, the amount of energy lost, and the costs related to those systems. And that's why we handle them a little bit differently. And similarly, for decentralized equipment, the costs of boilers for 10 buildings or for 150 buildings and their operations, it's going to be vastly different. So that's why we have kind of these two aspects where we have to do greater in-depth calculations. Alright, so we're going to stick to these defaults, realizing that we're going to come back to this to show that greater detail later on. The only thing we've changed then is to make sure that we've basically turned on this distribution network. We've said this does exist. We want to allow it to be used in the solution. We're going to go ahead and save this, and we'll spend more time on the technologies when we come back around to look at the alternatives. That's when we're going to be looking at those technologies as potential for their potential in the solutions. Alright, we can see that the little icons have turned green here. I'm going to go back over and make sure that there aren't any surprises. When we look here, we should see 0 distributed boilers. I'm going to scan down to the end with our new piece of equipment. We should have 4 boilers here. And we do. Nothing else has changed. We have no installation costs. That should be correct. We're going to look at the storage. We have a high temperature hot water network. That's important. If we didn't have it, there'd be no way to get that heat from the central plant to the buildings. So we want to make sure we can account for that whole path. Alright, so everything is fine here. You can't tell easily, but if you look closely, you can see that we're currently in the centralized buildings cluster. So looking off, there's a little box around it. We can also scan down to the decentralized buildings. And again, no surprise, we just changed the name here. Everything else is the same. So now we can continue on to the Constraints tab.